I'm going to present a general memory model based on nominal techniques and its application to the verified compilation of C programs. So memory model plays important roles in verified compilation. This figure shows the structure of a typical verified compiler. The source program P1 is compiled into the target program Pn through a sequence of transformations. To prove this compilation correct, you need to show every compiler pass preserves the semantics. For this, those semantics needs to be based on certain memory model. And we need to establish memory invariance between the memory states for each compiler pass. The state of the art is the block-based memory model for the COMSAT verified compiler. In this model, a memory state is a collection of disjoint memory blocks, each with its unique identifier and a linear address space. A pointer is a pair of block identifiers and offsets into that address. And the pointer arithmetics are performed by adjusting the offsets while keeping the blocks unchanged. This provides a very simple notion of isolation between different memory blocks. The memory invariants are described as injection functions, which are partial mappings from blocks to blocks plus offsets. The bottom right figure shows an example where the source memory B1 is injected into the beginning of the target block B prime by the function J, and the B2 is injected to offset delta in B prime. And the B3 is dropped by the compilation, so it is injected into nothing. This memory model is still quite primitive in the sense that block identifiers must be positive numbers. And a special identifier called the next block indicates the next available block to be allocated. The blocks that has already been allocated are called valid blocks, and they must be numbered from 1 to next block minus 1. For example, at the beginning, next block is always 1. As you allocate more memory blocks, the next block increases. And the allocated blocks must be numbered continuously. This creates a lot of problems in describing the memory space. First, there's no way to distinguish between different memory regions because every memory block are given a positive ID. Second, the continuous numbering of blocks actually brings unnecessary dependencies between memory blocks. Let's take a look at the elimination of unused global variable transformation in COMSAT. In this example, the second global variable is not used by the program, so it is dropped by the compilation. As a result, in the target memory state, every memory block that is allocated after block 2 in the source is shifted by -1. Even for the stack blocks, which are not supposedly to be touched by this transformation. So this results in an unnecessary and complicated invariant, which makes the proofs much more harder to understand. We also have a problem with the next block, which is shared by all the threads in a concurrent setting. This also creates problems in verification when you are compiling concurrent programs, as we shall see later. The problems we just talked about are related to the treatment of named resources in verification. The resources we're talking about are memory blocks. So we ask the following question: is there a more flexible representation of the memory space without those restrictions? And what benefit it can bring to compiler verification? Our answer is the nominal memory model, which is a generalization of the block-based memory model based on nominal techniques. It provides a flexible representation of block identifiers and completely eliminates the dependency and constraints we mentioned before. Furthermore, nominal memory model is compatible with all the existing mechanisms, for example, the memory injections. Based on the nominal memory model, we develop a nominal COMSAT, which is the general framework for verified compilation, in the sense that the proofs are abstract over the nominal interface. You can provide arbitrary complex instantiations to this interface, it will still works. So through this instantiation, we can generate many useful applications. We are going to talk about the two applications. The first one is to support intuitive and precise memory environments with structured memory. And the second is to support verified compilation of open modules into realistic multi-stack machines. So our work is based on nominal techniques. In nominal techniques, the names are denoted as atoms, which are drawn from countable infinite sets. And renaming is described as a permutation of the atoms. A set of names supports an object if the following condition satisfies. This basically means all the names that X can depend upon must be in the set A. So a name is fresh to X if it's not in the support of X. So the key idea is that if we treat the memory state as named objects and the block identifiers as names, we can do the following generalization. First, the atoms can be used to generally represent block identifiers. And permutation of names is equivalent to memory injections that does renaming of blocks. And the supports can generalize the valid blocks. And finally, the freshness conditions can generate the next block. Note that we have not tried to exploit the analogy between the permutation and the injection, because in our settings, the context is fixed and there's no permutation. Let's take a look at the nominal memory model, which is just an abstraction of the block-based memory model with the following interface. Here, the blocks can be any type with decidable equality. And the support can be any type that satisfies this abstract interface. Particularly, we need a fresh block method which generates the fresh block relative to a support. And there's also a valid block method for checking the validity of a block relative to a support. There's also Wolframness properties about support, which I'm not showing here. With this interface, the block-based memory model simply becomes one of its instances. The block type is instantiated to a positive numbers, and the support is just a list of valid blocks. And the fresh block method generates the next variable block, and the valid block simply checks the membership. Now let's recall the problems we have mentioned before. The nominal memory model completely solved them. First, we can instantiate the block type to classify different memory regions. Second, we can instantiate the support type to separate the disjoint memory regions, so you don't need a continuous numbering of blocks anymore. Third, we can implement the fresh block to provide the different strategies for allocation in different memory regions, so there's no global constraints. With those generalizations, all the operations, properties, and proofs in the original memory model still remains mostly unchanged. So our approach is not intrusive. Based on the nominal memory model, we developed a complete extension to COMSURT. The structure, it is called a nominal COMSURT. The structure of a nominal COMSURT is basically the same as before. The only difference is that our memory states are based on the nominal memory model, and we still have the same memory injection, except the block identifiers can be instantiated to different types. Thanks to the abstractions, all the proofs will hold on any instantiation of the nominal interface. So with the nominal COMSURT, we can develop useful verification techniques by instantiating the nominal memory model. The two applications we are going to talk about is to support a verified compilation of memory transformations through structured memory, and also the contextual compilations to multi-stack machines. The key idea for the first application is to instantiate the blocks and supports with rich memory structures. The memory space is divided into global space and the stack space. It is indicated by this support type with two fields. The global blocks are simply a list of static names. The stack space is organized into a tree of stack frames, which mirrors the core graph. The right-hand side shows an example. Every node represents a stack frame allocated by some function. And every stack frame contains a list of blocks for local variables, each of which has a locally unique identifier. The edges represents function calls. They are numbered by the order that happen at every level. So this tree structure is represented by a data structure type called S-tree. Note that we treat heap as a part of the global memory managed by some kind of allocator. The block type is defined as an inductive type with two constructors. The stack block takes three arguments. The first argument is denotes the function that allocates this stack block. And the second argument denotes the path from the root to the stack block. And the third argument denotes a local identifier for the stack block. So this shows an example of a stack block in the red cycle. So this stack block is allocated by function g, and it has a path 2, 0, and a local identifier 1. With this rich memory structure, we can actually represent the memory injections as statically defined functions. We go back to the elimination of an unused global variable example. Previously, to prove the compilation correct, we need to show there exists a certain memory injection, but we don't know what it is. Now we can actually explicitly define this memory injection as a partial identity function. It is shown on the right by this struct memInj function. It checks if a block is in the domain of the injection function. If so, it will map it to itself. The check block method simply checks if a stack block is valid or not. But for global block, it will check if this block is actually in the target environment. If not, it means this block has been dropped by the compilation. Otherwise, it should be preserved. So this very explicit definition of memory injection makes the proofs much more easier to understand. Second, we observe that many transformations on memory only focus on certain local memory regions, and the statically defined injection functions can precisely capture those local transformations. We take the merging of the stack allocated variables as an example. This compiler path merges the blocks for the local variables into a single block, and it is performed frame by frame. So this is defined by this structural injection function. It first checks if a block is valid. If so, it will call the unchecked memInj function. The unchecked memInj simply maps global variables to themselves. For the stack variables, it will call a function to find out the offset at which the source stack block is injected into the target block. It then returns the target stack block together with this offset. Note that the only difference between the source stack block and the target stack block are their local identifiers. It means that the stack tree, the structure of the stack tree is unchanged, only that certain local blocks will be injected into the first target block in the corresponding stack frame. With this idea, we have implemented a structured memory for the whole compilation path of a nominal CompSert. This results much more intuitive proofs for the memory transformations in CompSert. You can find out more the details in the paper. The second application is related to improving verified contextual compilation. Contextual compilation means compilation of open modules in certain context memory. It has been investigated extensively before, but there's still problems with contextual compilation of multi-threaded programs. First is how to support stacks that can grow independently for different threads. We take the compilation of certified concurrent abstraction layers as an example. In this example, every thread has its own stack represented as a linked list of stack frames. The dummy blocks, which are the blocks with diagonal lines, must be allocated to maintain a consistent view of next block for each thread. For example, when the thread 2 allocates block 3 and 4, the thread 1 must allocate 2 dummy blocks so that its next block increases and so that the global shared next block state will be consistent. Although this approach works, after the linking, the two stacks for two different threads are interleaved with each other. So it is unclear how to untangle them with the further compilation. We also would like to support compilation of different threads into continuous and finite regions, which matches the realistic machine. But it's also unclear how this can be done with this approach. Those problems can be solved by extending nominal COMSURT. First, let's take a look at how to support finite stacks. Previously we have developed a stack-aware COMSURT, which for the first time support a finite and a continuous stack in COMSURT. It is done by proving stack consumptions is not increased by the compilation. The key technique is to instrument the memory state with an abstract data type called an abstract stack. We observe that abstract stack simply describe the properties about the stack consumption. So it should be able to be absorbed into the nominal memory model. That's exactly what we have done. We have developed a stack-aware nominal COMSURT, which with this new support type. This support type has an extra field to represent the stack ADT. With this very simple extension, we can significantly simplify the proofs for the preservation of the stack consumptions. This is described in the paper. With the stack-aware nominal COMSURT, we can further extend the compilation chain so that it can compile C modules all the way to a realistic assembling programs that has a finite and a continuous stacks. Now we can do a simple extension by expanding the stack tree and the abstract stack to be a list of stack trees and abstract stack ADTs. There's one stack tree and a stack ADT for every thread. And we added a new field called the thread ID into the support type, which represents the active thread that should be operated upon. With this extension, we have for the first time supported the compilation of C modules all the way to assembly language based on a realistic multi-stack machine. This is called a multi-stack COMSURT. The multi-stack COMSURT can be directly applied to solve the previous problem. In the new solutions, every thread has its own separate stack from the beginning. So the linking of those different threads is simply putting them together in the memory model. And we can very easily compile those separate threads into independent and finite stacks, which will match the realistic machine model. So this concludes our applications. The loss extensions has been implemented on top of COMSURT version 3.8 in Coq. The nominal COMSURT is very moderate extension to COMSURT, only added about 0.5 of code. It is implemented in 1 person month. The nominal COMSURT with the structured memory space takes a bit more effort. It added about 2.5% of code to COMSURT, and it takes 2 person months. And the multi-stack COMSURT, including the stack-aware nominal COMSURT, is the most complicated one. It takes about 3 person months and increased about 10% of code to nominal COMSURT. The full artifact can be found online, and you can check them out at your interest. So in this talk, I have presented the nominal memory model, which is a principled generalization over the block-based memory model that provides a flexible way to describe the memory space. On top of this, I have presented the nominal concept, which is a general framework for verified compilation. In the sense, you can instantiate the nominal memory model to get different instances of concepts with different memory structures. Those instantiations have useful applications as we have just discussed. Note that regardless how complex of those instances are, the existing proofs, including the memory injection-based proofs, still remains valid. In the future, we would like to combine the nominal memory model with the techniques for general compositional verification, such as COMSAT-O. And we also want to support transporting proofs based on a particular memory structure to a different memory structure so that we can actually reuse the proofs for verified compilation. And finally, we believe the nominal memory model is also useful for program verifications in general. And this is a topic that we are also investigating. If you are interested to find out the details, you can read the paper and also download the artifact on GitHub. And thanks for your attention.
Thank you very much, Yuting. Questions from the audience? Locally or online? There doesn't seem to be anybody. I think we're all very much impressed by all three talks, so no questions. Yep.
Hi, I'm Yixuan Chen from Yale University. I'd like to ask a question. We have just had a few. We have just had a talk about VIP where they introduced a new pointer model that can verify pointer integer casts. Would you think that memory model would fit into the nominal memory model that you just introduced, and also verify COMSAT based on that? Thank you.
Yes, thanks for the comments. Yeah, we do believe that there are a lot of compatibilities between different verification techniques with this memory model, because our memory model provides a very general interface. So it should be in nature to be able to be integrated with other verification techniques.
Thank you. Any more questions? No? In that case, let's thank the speaker again. In fact, let's